Interferometric synthetic aperture radar, or INSAR, is a family of remote sensing techniques used to measure ground deformation. SAR is an active ranging technique which uses pulses of microwave energy transmitted and received back by an antenna. It can be used in day or night, and in all weather. Several wavelengths are used, ranging between 3 and 20 centimetres, referred to as X, C and L band radars, although there are others. Shorter wavelengths give higher spatial resolution and greater sensitivity to ground change, whereas longer wavelength allows penetration through vegetation canopies, sometimes into the ground materials too. The radar wave interacts with the ground and is scattered back to the sensor and measured as variations in amplitude and phase. And the measured fraction of phase is proportional to the distance between the antenna and the ground and therefore contains ground elevation. If we compare two SAR observations of the same target from different positions, we can derive the interferometric phase between them to extract the topography with an accuracy of tens of metres or so, and this is INSAR. If we then use SAR observations separated in time, such as before or after an earthquake, we can extract the differential phase to measure ground displacement at centimetre accuracies, and this we call differential INSAR. Man-made objects scatter the radar beam strongly and consistently in time and space, and we call these point or persistent scatterers, whereas natural land surfaces change and scatter diffusely and irregularly, so these are referred to as distributed scatterers. Orbiting satellites allow us to observe the scatterers over prolonged periods of time by combining many SAR observations. The persistent scatterers provide stable signals throughout those observations, and this allows us to track millimetre-scale displacements of their location, a technique we refer to as time series persistent scatterer INSAR. INSAR therefore allows us to precisely measure small ground motions, such as those caused by tunnelling, construction and water extraction, and it therefore has an important role to play in hazard monitoring and environmental security.
Over the last decade or so, INSAR has gained recognition within the civil engineering community as a powerful and cost-effective tool for detecting and monitoring ground deformation above tunnelling projects, particularly those in urban areas. In London, INSAR was used following the construction of the Jubilee Line extension in the 1990s, when subsidence along the line of the tunnel was observed. During the Crossrail project, for which tunnelling took place between 2012 and 2015, INSAR was also used as a post-construction monitoring tool to complement ground-based measurements. The INSAR data revealed a roughly east-west orientated string of subsiding areas across central London, where the ground above the Crossrail tunnels had settled following excavation. What was unexpectedly observed in the INSAR data was the presence of a fault in East London. During excavation of Crossrail's limo shaft, water was removed from the ground in a process called dewatering. The INSAR data revealed a bowl of subsidence that is truncated at the western edge. It appears that a strike-slip fault, known as the Lee Valley Fault, impeded the flow of groundwater. The ability to use INSAR to identify these hazards is highly beneficial during the depth study and ground investigation phase of a construction project, particularly as geohazards in London are challenging to map by traditional methods due to the dense urban fabric. Another example of a geohazard identified by INSAR is from a retrospective analysis of the Lee Tunnel, which identified a drift-filled hollow, which is a steep-sided depression in the bedrock, infilled with sand or gravel, beneath Newham Hospital in East London. The Lee Tunnel is the first part of the Thames Tideway Super Sewer project to be constructed. We found that localised subsidence had occurred on the eastern edge of the hospital going back to at least 1992. The drift-filled hollow was not found during ground investigations prior to the construction of the tunnel, but was intersected during tunnelling, causing delays. We concluded that had an INSAR analysis been undertaken prior to tunnelling, the drift-filled hollow could have been identified prior to construction. On a broader scale, INSAR also reveals the geometric arrangement of London's fault network. London's surface moves as a series of discrete blocks coincident with major elevation changes in the chalk subsurface. Using a combination of borehole data, traditional geophysics and INSAR, our research group has compiled a new fault map for London.
Urban environments appear very differently to rural ones in the radar data. In urban areas, there are a high number of so-called persistent scatterers. These measured features might be the corners of buildings, metal structures, or any other geometrically stable feature, which acts as a strong reflector of the radar signal. The stability of persistent scatterer signals and their high signal-to-noise ratio facilitates very accurate measurements of ground movement. In rural areas, however, persistent scatterers are scarce and INSAR accuracy suffers as a result. The noisy behaviour of vegetation is a particular problem for our sensitive measurements. As a result, so-called distributed scatterer methods are being continually developed in order to improve the range of terrains to which INSAR can be applied. These methods identify areas with similar statistical behaviour in the data. They then filter these areas to minimise their signal's noise. With these additional steps, INSAR results can provide millimetric accuracies in rural areas as well as urban. Here we observe ongoing settlement and consolidation behaviour of recent backfill and spoil, associated with the Foss of Ran coal mine and land reclamation project in South Wales. Recently emplaced material in spoil heaps and infilled voids appears to be settling at a rate of around 1 centimetre per year. A steep west-facing slope is measured as moving towards the satellite at a similar rate. This indicates ongoing movement of the material downslope. INSAR is also proving to be a valuable tool in investigating coastal processes. Here we focus on a rotational landslide at Cow Gap, an area of chalk cliffs near Eastbourne in the UK.
The advent of persistent scatterer interferometry has truly transformed both our understanding of the geology of London and also how we measure and monitor engineering in the capital. But what does the future hold for this technology? One of the problems that we have with the current data is that they are only acquired every few days or a week or more. And so we can't resolve small timescale changes. For instance, when we're tunnelling underground under London, building Crossrail or Tideway or something, we want a much finer resolution timescale. And currently there are swarms of satellites in planning to be launched into low Earth orbit over the next few years. And these satellites will hugely increase the rate at which we acquire INSAR data, and therefore the rate at which we can monitor ground movements, so that it will be useful as a monitoring tool in almost real time, not just as a tool for understanding what happened when. Coupled with that, we are miniaturizing the technology and putting it onto drones so that we will be able to fly closer to the ground and get very high resolution monitoring data as often as we want it, wherever we want it, where we can fly a drone. And that will again also transform our ability to measure and monitor both geological change and the engineering that goes with it. Finally, the sorts of techniques that we're applying are evolving all the time. And one of the difficulties that we have with persistent scatterer interferometry is that it's very difficult to achieve in rural and vegetated areas where the weather is constantly changing, the ground moisture is constantly changing, and of course plants are growing. And we are developing our algorithms and our tools to work better and better under these conditions, using wider ranges of data sets and using better corrections. So you can be sure in the future we will be applying the techniques that we have currently in London across the country and worldwide.